first speaker of the session is Ekhard Salje from Cambridge University, who will tell us about avalanche mixing.
Well, thank you very much indeed. I can see some vacancies. Of course, these would be the people have a problem and they can't hear you. So anyway, very glad to be here. And first of all, congratulations and many thanks to the local organizing committee, not only to have secured so much excellent funding, which we all like, but also to have this nice building. And I was very skeptical in the beginning whether we make it here, but obviously we did, and the weather is wonderful, so that's great. So I should say what I'm talking about today is avalanche mixing. It's a problem I've been working with Anthony Planes and Eduard Wiebes for a couple of years, something like that. And then I do a lot of experiments now on avalanches in China, and that is very much related to applications, so not just fun, but also fun. And my main collaborator is Yang Yang, and he's in Chongqing. So it all started in all these materials which become sort of key materials have a history. I mean, Vico had a history because we were interested in fillers for aircraft wings. You know, the stuff you put in there, I mean, fairly stiff stuff. And the aircraft industry was very keen to put some SiO2 in because it doesn't burn, it's fairly safe. And they used Vicor, and then we used Vicor for our experiments, and that's great. Right now it's coal, and where it all started with. And I must say, as a child, I was sent down the mines once. It looked like that, and it's a horrible experience. I mean, don't do it if you don't have to. It's very, very hot. You can hardly breathe because all this coal dust goes into your lungs. But the worst, I thought, was the noise. And the noise is not just from the equipment which is in there, but the noise comes actually from the rocks. I mean, it's constantly making this crack, crack, crack sort of thing. And the workers down there, they tell you immediately, don't put your hands on the floor because something might fall on it and then they're broken. If you keep them like that, it's much safer, and things like that. And they had a good experience that, you know, when something locally might collapse, sometimes there's a precursor effect, but quite often there's not. And therefore, you know, years of experience which went in there. I was much more delighted when I became a bit more interested in earth sciences. Then coal suddenly was this. This is actually coal. It's really coal. It's this dense stuff. And it was very, particularly, it's called jet. It's a jet jewelry, which was very, very highly priced in the 19th century. And it was the jewelries of widows. So when the husband died, they had to show that they were in sorrow and so forth. So they put this sort of jewelry on. And it was incredibly expensive. And only in France, so that still nowadays exists in Britain and in the US. It's actually used by quite a number of people. It's very expensive. There's a French jewelry, which is also called jet, which is an imitation by black glass. So that's not the real thing. But this one is really pieces of coal which are polished and so forth. They're so dense that they withstand handling and all that sort of thing. So I had to rewrite all my introduction because Edward gave it already, and I didn't want to bore you with it. So I show you a few other experiments. So that is one of the instruments we use in China, and China is big and the instruments are even bigger. They build sort of coal mining and iron mining instruments for testing whether they collapse, the mines collapse and so forth, with chunks of material which are massive, absolutely massive. And they put them into these machines which are quite often used for compressing parts of automobiles. So it's really heavy stuff. So here is the sample. This is a small version, but you know, this one is taller than I am. Here is the sample. Here, the samples can be very, very big. I mean, they can have diameters like that and height like that. And you can put in as many acoustic emitters, AE detectors on there as you like. So they're very well equipped. And then when you do this experiment, of course, we have learned from the Barcelona group that all what you do, you have to do very patiently, very slowly. And so in Barcelona, they have the same, this pulling thing with water in there. And here it's oil. It's the same stuff. Here's a pocket, basically, and you drip oil in there. And that means the lever coming down here increase the force to pull it down, and this increase of force is incredibly slow. You can run an experiment for a week, or even more if you want to. And therefore the individual jerks are quite well separated. And that's what we need for these instruments. So what you have here is a jerk spectrum. You can see it's uniform after, we call them super jerks. Some of you use it, others don't. The super jerk is just the biggest jerk in a sequence. When there's a bigger one, that becomes the super jerk, and so forth. So you can see here, this one, the 1 to 13, is just an increase of intensity. Then the next big jerk is 14, 15, 16, 17, and so forth. And so quite often you have 20, 30 super jerks. And it's a very convenient way. There's no big theory behind it, but it's a convenient way to split this entire area up and then say, is there something different from the beginning to the end of the spectrum, and so forth. So you do that in a way quite automatically. So if you take anything from 13, the beginning is clearly to get the sample right. You measure, for instance, coal. And this one is the Chinese stuff. This one is the Barcelona stuff. Whatever you do, you get a very good exponent. I mean, the ML curve is very flat, and you get an exponent of 1.42. So you're quite close to the mean field level. When you do that as a function of the early collapse and the late collapse with the superjerk stuff, then you see they're indeed not exactly identical. And so you see the early ones are the red points, which are slightly steeper. So the exponent is 1.5 about. And the late ones are these 1.32, 1.4. So all the other data for the later experiments, I mean, once the experiment is settled, we get the same results. So there's not a big problem. You can see the ML curves here also, they are quite different. So the effect is real. In the beginning we have a slightly higher exponent. The question is, of course, where does it come from? And we heard a lot about that already yesterday. Now what we can do is to localize the centers of the jerk emission very easily. And if you do that, then you find very much at the beginning, of course, the surface does something because the plates on the surface are not perfectly matching. Once that's done, that's a very, very early superjerk. But then the main stuff is this one. So that's all the data which with the 1.51. They look like that. And then, of course, they accumulate, they localize, and so forth. They go along the shear plane, and that is the lower exponent. And all of them are in this regime here. So it's I find it very convenient to do that. You could take the spectrum and just take an equivalent or equidistant intervals, but if you do it this way, that's quite good. So this one is almost history. So these are the data. We are happy or not happy. That's what it is. The question then was, if you plot the exponent here, you have a little bit like 1.5, something a bit bigger than 1.5, and then 1.3, 1.4 here. So the early K is the number of the superjerk, the so-called rank. So at early ranks here, we have a larger exponent. Here we have a smaller exponent. And of course, when I first showed that to Kuhn and Ferenc and so forth, clearly he loved it because all his models show this change of the exponent, where I was never quite convinced that that is the right mechanism. I'm sure you're not convinced of that at all. No, okay, so we agree totally on that. So the question was then, where does it come from? Is it really coming from this dynamic rescaling and so forth? My hypothesis in the paper, this paper is now a couple of years old, was to say, no, in reality, we have only two values, and that might come from the heterogeneity of the coal. There might be some softer material in there, which gives you this one, or it's a localization, not localization. But in fact, we have only two exponents here we have to take seriously. That's the early one and the late ones. So the question is, what is the stuff in the middle? And of course, the stuff in the middle, if you have a little bit of fantasy, you say this one is actually not a continuous change here. It's actually the superposition of the two others. So you have probably both power laws here in this area here and with different ratio. And then if you fit it somehow as good as you can, even with ML, whatever you do, you get something which effectively gives you an effective exponent which has actually nothing to do with the behavior. And so that was the hypothesis. Now, well, I'm a bit older than most of you, but those in solid-state physics have immediately all bells ringing, because that was the start of the effective medium theory stuff, which dominated, you know, the 1980s, I guess. So we went on a little bit more. So when you have two different materials and you measure a macroscopic parameter, which depends on the mixing, how you mix, what mixing properties you have, what the initial properties are, and so forth, then you can calculate what the mix will be. And it turns out that, you know, Voigt and these guys did wonderful equations. They're very simple, but as soon as you have something a bit more complicated, it's actually extremely hard work. And in particular in my field, say ferroelectrics or ferroic materials, it's bread and butter. If you don't do it, you really get wrong answers. So you have to know what the effective medium approach is. And so the idea was then to say, okay, let's first of all do it in a synthetic way, and that's what we did in this paper here, which is already also a year old, a bit more than a year, with the Barcelona group. So there we simply said, okay, we take two power laws and add them. Of course, we then put the noise in, so we do a synthetic jerk spectrum, whereby part of the material has an exponent of 2 and one has 1.5. We just choose 2 and 1.5 out of the blue. There's nothing fundamental about that, but the contrast 2 and 1.5 is very big. Most of our effects are less than 2. If we can't see 2, we have a problem. I mean, if we can't see this contrast here, then we have a problem. So when you do that, then you find the PDF looks like this, right? With a reasonable amount of noise. And of course, you see immediately, of course, this one is not a power law, because you have a power law and you have another power law and you have this upwards bend, right? The upwards bend is the key element I'm talking about. If it's upwards bend, it's not one power law, it's two power laws, or however. Now, the point is that if you have these data, you know, there's quite a few decades here, then you might just about see it. But if you give your student a little job to do something, to measure, and he sees that, he puts one line through it, obviously. And then he says, okay, we have a little bit of something here or not. So the question is, would you really see that that one is not a straight line? You know, where is the deviation? So, okay, so we are talking about this small effect. We can make the effect just empirically bigger if you look at the ML curve. Now, ML, I'm not talking about ML here in any philosophical way. I'm just saying it's a tool, and it makes it easier. If you take the jerk spectrum here, you don't have to think about the binning. So you do the ML exponent, and then you see, okay, you start at low, and then you go up, you have a peak here, and then you go down in the ML curve to the second exponent. So there's up to, I mean, it's not terribly intelligent, right? I mean, this one, the ML curve of that one. And the dotted line here is the theoretical curve. You can do analytically, of course, then, whereby the upper exponent here, the 2, is never reached. So it's an upper bound. So the highest value you measure is still below the upper bound of what you have for the highest exponent. And the lower bound you reach. I mean, you can go to the lower exponent, but you can't go below that. So if you see this sort of, I mean, the fingerprint here is the big peak and then the decay. That's what we are looking for. You really want me to explain that? You know that. The usual integration, I do that. We do that later. Maximum likelihood. The word ML is the problem. Maximum likelihood exponent. All right. Yeah, not machine learning, my God. Yes, in Los Alamos it would be. Next time is, if I say AI, then it's artificial intelligence. I know, all this. we are all in the same boat. Okay, so now in the tradition of the good old effective medium theory, I start with the void example. So I take two samples. One is coal and one is sandstone, put them in a sandwich configuration, stick my acoustic detectors on these two and compress them together. That's the first level. When you do effective medium, you do that. And now, I mean, the addition is very easy, and you have jerks here, you have jerks there, and they're the jerk spectra of the two. This is not an easy experiment. I mean, it might look easy. It's quite easy mechanically to get it right, but what you have to do is you have to find materials which roughly, in this case very well, collapse at the same critical point. So the coal has to be quite hard and the sandstone has to be quite soft. This is a very, very porous sandstone to match the coal. So, I mean, you can do any you like, but of course that one would be the most interesting one. And you see here, this one is the energy from the sandstone, that's the energy from the coal. The collapse here, the precursor is much bigger there, but not in sandstone, and so forth. So when you then take all the data, I mean, all what you measure, put them in one data file, and then do the maximum likelihood curve, then you see something. Oh, sorry. Oh, gosh. You do the, first of all, the PDF. So you have the PDF here. These ones are two sets of experiments where a very kind referee asked us to do it twice with two different sets of equipment. So one is the Chinese one and one is the one in Barcelona. And you see one has much higher energies, the other one has lower energies. But you see the curves look roughly the same. So you come from, if you look here, you come from 0, you go up. Here's the upper bound if you extrapolate, and then it goes to the lower bound here. So you have this peaky kind of thing here in the beginning, which is the fingerprint that you have mixing of two avalanche processes coming together. And if you look at your own data, you will find actually in quite a number of data, when you look very carefully, that they have this negative slope here after the first peak. Any of them. Exactly, yes. It can, I mean, quite often, I mean, the suspicion you have, you have two mechanisms which are going on. And a good way of finding that you have two mechanisms is this kind of behavior. So, I mean, we are starting now with two power laws and do it this way, but absolutely. It does. I mean, the not 1.5 here is 1.65 for these coal data here. That's the higher one, and that's the lower one. They, of course, we know individually because we take each of these samples and measure each of the samples separately. So these curves are totally fixed. There's no fitting in there. I mean, this one is the only thing which you fit from the data, but they fit with that end point and that end point. So they. Yeah, exactly. You have to be careful. You have to have enough data points in there. Absolutely. Yes. Okay. So then the question is, are we now, I mean, have we mimicked the void effective medium theory? Of course we haven't, because we're in a dynamical case. So the question is, do we have avalanches which effectively start in one medium and go into the other medium, or even start in one medium, trigger in the other medium another avalanche, and then see how that comes. Now, in all our experiments, we can measure that. I mean, here you have this scenario, you have avalanche source here, one propagates outwards, the other one goes into the other medium. It can do some stuff there. And then we have our detector here and we have our detector here and so forth, so we can measure them separately. When you look at the coincidence, we see that the coincidence between two neighboring jerks, then we find that we have actually quite a bunch of data which are at time intervals less than 10⁻³ seconds. So we have, milliseconds and less. We can go to 10⁻⁵ seconds. 10⁻⁵ in other experiments are very common. So suddenly you have a lot of events here which do not come. I mean, so it's one which triggers off in coal, and then a little bit later, 10⁻⁵ seconds later, it goes into sandstone or vice versa, and so forth. So these are all these data here. The gray data are all the points which are, they asked me a question, which are in one and the same medium and so forth. So, okay, now we go one step further and say what happens if we don't have sandwiches but we mix the material. So we deliberately make material which is mixed, and that is magnesium-holmium alloy, which is used for the Chinese spacecraft stuff. And so here is the material. It has holes in there. The composition varies quite a bit. It hasn't got grains, but so almost grains, and it's full of dislocations. When you look with the TM, you don't see twinning. So the stuff is not twinned, but it has lots of dislocations and has holes, and that's, of course, for us very nice, because we can see how the jerk spectra look like. So we know what the elementary processes are. Here we have 2.3 million data points, which is actually a pain. I will show you in a moment why that is a pain. If you have tension, you have fewer. So you have here, again, the super jerks. You can analyze that. Here, the initial state is quite different. And as it turns out, this one is the stage when the holes collapse. And here are more the dislocations moving. So when you analyze them, you get very, very nicely. Here now, the mixing, of course, is ideal. You find this peak. It goes down. The individual hole we would have guessed is about 2 here, and the dislocation are 2, and the hole collapse 1.4. In compression, you have more data, and you have a little bit the dependence on the history. Of course, we are saved here because the collapse of the hole gives a much bigger AE signal than the dislocation. I mean, they're different by orders of magnitude. So if we just take the big data and the small data, we can measure them separately. Take this as an example. This one is the dislocation part. This one is the hole part for the maximum likelihood curve. So in this case, we can separate them. And of course, we cannot do this coincidence stuff. I mean, because we haven't got the separate detectors, and you can do the same for waiting time. Now, let me show at the end a case where we want to know that the superposition of two processes happens, but we can't see it. Okay? I mean, that's the other big area. That is barium titanate. It's one of my bread and butter material I have to work on almost every day. So that's material for ferroelectric memory device and so forth. Now, when a ferroelectric domain boundary moves, it carries strain. The 90-degree boundaries carry a lot of strain. So when they come out and they hit the surface, whatever they do, they have acoustic emission signal. I mean, theoretically absolutely clear, but we have an equal number of those who carry strain, the 90-degree boundaries, but the 180-degree boundaries have no strain. They're not twins. They're just ferroelectric domain boundaries, and the number is about the same. But because they don't carry strain, they do not generate any AE signal. So the question is, what can we do here? And first of all, of course, the big thing was to see anything. I mean, we tried for 3 years about or whatever to get any AE signal out, and we couldn't, but now we can. So here's the ferroelectric hysteresis, and you see whenever the hysteresis is steep here, you get lots of data, lots of data. We always do it several times, many times in fact, whereby the first one, the virgin crystal, is always a little bit different, and then the other crystals settle very quickly to an exponent. And you can see the exponent here, 1.65, is the exponent for barium titanate in steady state. But you see there might be a little bit, but I mean, there's not really a peak. That means the other part, the 180-degree boundaries, which we know electronically are happening, are actually not contributing to the acoustic emission signal, which is good. So if we have something which shouldn't do anything, it doesn't do anything. So and then you can do all the scaling. In this material, it's really very nice because we can the duration, for instance, in this case is very easy to measure because electronically very easy. So that is beautiful. And then in the end, we can get the general scaling relationship. In this case, works really quite well. So let me summarize the take-home message. You may or you may not, but in many cases, I guess you have several mechanisms in a material which coincide, which happens at the same time. And I would say in martensites, for instance, you have dislocations and you have twinning. These are two. But most material, many materials, certainly most we are looking at, are also porous. They have a little bit of porosity. If it's only 1 or 2% as you have, it doesn't matter very much. But if you have 20 or 30 or 40% like we have, then it matters an awful lot. And you want to know, okay, how is the material behaving? I mean, the material, the macroscopic response is the sum of all these responses, and you want to know what comes from the porous collapse, how much is dislocation, how much is twinning, how much is surface near instability, electronic instabilities, and so forth. And they all have their own fingerprint. When you put them together, then the first thing you find, I mean, if you have two, let's say, you get this peak in the ML curve, which is really a fingerprint we didn't think of before. But now that we are looking for it, we find it quite often. So that is quite a useful thing. And otherwise, you can see that this superposition, simple superposition, is a good first solution. But it's not the final solution because you have this point that something is generated in one medium and then is actually coming out in the other medium and so forth. And that's the effective medium in dynamical systems. Thank you very much. Yeah.
You said that one event in sandstone, let's say, could trigger something in coal.
It might trigger. I didn't say it would. No, I didn't say it does. I mean, what I do is exactly where it's not triggering here. In this case, it starts in coal and comes out in sandstone. Of course, there are quite a few of those. But it's not triggering another avalanche in sandstone then. Not in this case. I didn't say that. I haven't. I looked for that very systematically and haven't found a single one. You're happy with that, I'm sure. Yeah. No, sure. But it's not, we haven't seen that. No, it's not much larger. It's pretty close to mean field. 1.3. Oh, yeah, for the duration. Yes. That one is the Omori law, and yeah, it works okay. Yeah. It's -1. I mean, the Morley coefficient is -1. The exponent is -1. And the data look very good. I mean, you can see that here it comes slightly off, but we have, 1, 2, 3, 4.5 decades before it comes down. Yeah. Yes? Yes.
especially when you actually re-stimulate fault system that was pre-existing. So you find two populations, and this is
Absolutely.
a well-known case.
Yes, yes. And that's partly what we had in mind. Exactly that. Yes, yes, yes. I mean, anyway, I mean, if you look at the fault distribution, I mean, what you have in the mine and so forth, then you could potentially go so far that you can say you have a big one here and you have a small one there, and whatever comes out if you integrate them out. But we are not there.
Yes, one last question.
No, but I mean that really depends on your tectonic setting. I mean, you really have to have a fault system that is close to criticality, and you stimulate this. Yeah, that's what I think here as well.
Mm.
So that's not systematic anymore, but it's
Okay.
Okay, I think we have to move on, so let's thank the speakers.
Well,